Okay. Today I'd like to focus on fully differential single stage amplifiers. The last two lectures we talked about single-ended single stage amplifiers. Now we're talking about fully differential single stage amplifiers. I'll talk about general differential analysis. I'll talk about the 5T op amp. We're going to synthesize that 5 transistor op amp. I'm going to talk about biasing with common mode feedback circuits. I'm going to talk about common mode and difference mode analysis. If I talk fast enough, I'll talk about common mode gain and overall transfer characteristics. So that's the agenda for today. Review from where we're at. We talked about fundamental amplifier design issues in the first 2 lectures. Then we're looking now at single stage low gain amplifiers. We've already looked at some with single input. We're looking at ones with differential structures as well. After we get done looking at single stage low gain amplifiers, we'll look at single stage high gain amplifiers. And then we'll look at 2-stage amplifiers and then other ways to enhance the gain. So here's where we're heading. So we're looking at differential input structures right now, as I've shown here. And what we're going to show is that the differential input op amps can be readily obtained from the single-ended op amps. We're also going to find that the performance characteristics of the differential op amps can be directly obtained from those of the single-ended counterparts. So we won't have to go back in and reanalyze the differential structures. We're going to, by inspection, characterize the differential structures. We had some terminology that we introduced last time. We talked about a counterpart network. A counterpart network, I don't know if that blinking is good. The counterpart network of a network is obtained by replacing all N-channel devices with P-channel devices, all P-channel devices with N-channel devices, replacing VSS biases with V-to-D biases, and replacing all V-to-D biases with VSS biases. Very systematic way to create the counterpart circuit of any circuit. We had a theorem that said the parametric expressions for all small signal characteristics, such as voltage gain, output impedance, and transient conductance of a network and its counterpart network are the same. The reason they're the same is the small signal models are the same. If the small signal models are the same, then the expressions are going to be the same. But we're not saying that the voltage gains are the same. We're not saying the output impedances are the same or the input impedances are the same. We're just saying the expressions are the same. We had a theorem. Now these P and Fs that I've got here, what are they referring to?
Quarter circuit.
We call this a quarter circuit. And really this is just a 2-port. Here's the input port and here's the output port. So this is a quarter circuit, and this circuit on top here will likely be a counterpart circuit, but it could be another circuit as well. It's just a 2-port. So we start out with a circuit, F, and if it's a counterpart circuit, we will flip it over and replace the P's with N's and N's with P's and so forth, or if it's some other circuit. And then we reflect this half circuit over to make a structure with 4 elements in it. And we bias it in the tail with either a voltage source, VSS, or a current source, I bias. And the tail means along the axis symmetry. And we claim that if F is any network, and P is its counterpart, it doesn't have to be a counterpart, but P is the counterpart, then the following circuits are fully differential op amps, where the differential input V1 is V1 minus V2. And this kind of shows systematically how we put it together. We start out with a quarter circuit and a counterpart circuit, and patch them together like this, and then reflect them over from left to right, and we have our fully differential op amp. We also are going to show that most of the properties of the operational amplifier can be obtained by inspection from those of the quarter circuit. Now, for those of you who have been working on problem 5 in the homework assignment, we were analyzing a simple 5-transistor op amp. Are those equations simple to write? Yeah, probably. Are they easy to solve? No. There's a lot of work involved in solving that set of equations. And this suggests that we're not going to have to solve those equations. We're going to be able to write down the solution of those equations by inspection. Is that nice? So it does two things if we can pull this off. It saves the drudgery of solving the network, but furthermore, we can focus on getting insight in how the circuit performs rather than fighting the drudgery of solving the equations. So the implication is then that much of op amp design can be reduced to designing a much simpler quarter circuit. Once we know how the quarter circuit performs, we'll know how the whole op amp performs. Let's talk a little bit about general differential analysis. Here's our quarter circuit, our 2-port. And if I bias it by a current source, I can look at the small signal characteristics of this structure. Of course, it's supposed to be equivalent to the DC current source is an open circuit. I can replace this by a 2-port, and I can sum currents with this node. And I can observe that Vn and V1, the voltage across here, are the same. And if I solve these two equations by eliminating V1, I can find the voltage gain of this quarter circuit, and it's equal to minus Gm over SCL plus G. Here's the 2-port model of the quarter circuit. And what I've done here is I've summed currents at this node to get this equation. And I've observed that Vn and V1 are the same. From this expression for the quarter circuit, this is a frequency-dependent gain. What kind of a gain is this?
It's inverting.
It's inverting?
DC gain.
It's more than DC gain.
No.
This is a transfer function now, right?
Mm-hmm.
What does it happen at high frequencies?
Press 0.
It attenuates. In fact, what order is this transfer function? First order. We have another name for a transfer function that looks like this. What's another name for a transfer function that looks like this? Low pass filter. So our amplifier looks like a low pass filter. The DC gain is obtained by neglecting the S term. So it's equal to minus Gm over G. The bandwidth is the pole of the, or the negative of the pole of the low pass filter. So it's G over CL. And the gain bandwidth product for this structure, this times this, the G's cancel, and it's Gm over CL. Now, this is also an op amp. It's a single in and single output op amp. Does this have a high gain? Does this have a high gain? Or does it have a low gain? What? Depends on how big GM is. This quarter circuit could be a single transistor. It could be 20 transistors. So whether the gain is big or small depends on how big GM is and how big G is and how they relate to each other. How about the bandwidth? Does it have a wide bandwidth or a small bandwidth?
Depends on how big G is.
Depends on how big G is and how big
The load.
CL is. Okay? Remember, this is general analysis. It's not analysis of a specific circuit. It's an analysis of a 2-port model of that quarter circuit. Any two-port model of the quarter circuit, as long as the input impedance is infinite, that is, if there's nothing on the input port, can be modeled like this, characterized by two parameters, GM and G. If we chose to put a short circuit between the input and the lower terminal of this quarter circuit, and I look in at the output, I now see a what?
Output resistance.
I see a one port, don't I? And I see what's the equivalent going to be?
The output resistance.
It's going to be the output resistance of this quarter circuit. So I can replace small signal equivalent of this one port is now a conductance of value G, where G is the small signal output impedance of that quarter circuit. GM disappeared. Why did the GM disappear?
We shorted the clutch.
We shorted V1 out, so GM V1 was 0. So this was gone, so all we had left was G. Okay. So now let me look at the differential gain. So what I'm going to do is excite this op-amp. We claim this is a fully differential op-amp. We don't know its characteristics yet. We're going to get those shortly. I'm going to excite it differentially. So this signal will be opposite in sign. And the total input will be VD. So if the total input is VD, this will be VD over 2, and this will be minus VD over 2. This lower terminal here, I'm showing going to ground, but it could go to VSS. It depends on whether you want to call VSS ground or not. I know that this circuit is symmetric. If this circuit is symmetric, how do I know it's symmetric?
Voltage axis of symmetry should be 0.
How do I know it's symmetric?
Well,
I made it that way.
oh, I see.
I just copied it and flipped it, right? Okay? It's symmetric. So what do we know about the voltage at all points on the axis of symmetry?
It's 0.
They're 0. If you have a symmetric circuit and excite it differentially, the voltage at all points on the axis of symmetry is 0. If this voltage is 0, then I can look at the relationship between this output and this input without even looking at the right half of the circuit. I can look at the half circuit. So here's the half circuit. It's comprised of F network and the P network, the counterpart network. And this voltage here is 0 because it's on the axis of symmetry. I'm exciting differentially. So that's why I get a ground here. So this is my small signal differential half circuit. This voltage here is 0 as well because the small signal equivalent of VDD is a ground. Now, this circuit here is VDD, VBB is the biasing voltage here. This is basically input to the counterpart circuit. We shorted it out. So we know that the small signal equivalent of the counterpart circuit is now a conductance of value G of the counterpart circuit. So I put 2 on there to indicate the counterpart circuit. So this is a small signal equivalent of the counterpart circuit. This is a small signal equivalent of the quarter circuit. I can sum currents at this node here, and I get this equation here. And I can observe that V1 is equal to VD over 2. I now have 2 equations and 1 extra unknown. That extra unknown in the equation is V1. So I can eliminate V1 and find the transfer function. And here's what the transfer function looks like. V out over VD. V out minus over VD is equal to minus GM1 over 2 divided by SCL plus G1 plus G2. What have I found?
Open loop.
Open loop,
Gain.
differential voltage gain of the circuit. If I excite it differentially, this is what the gain looks like. If you go back to 230, we looked at primarily the difference mode gain of the op amps. We've got the difference mode gain of this op amp. It's characterized by three parameters. The output conductance of the counterpart circuit, the output conductance of the quarter circuit, and the GM of the quarter circuit. What characteristics of an op amp are probably the most important characteristics?
Gain.
Gain, bandwidth,
Gain bandwidth.
gain bandwidth product. Right? Can I get the DC gain for the circuit?
Yes. Yeah.
Yeah, this ratio is the DC gain. Can I get the bandwidth? G1 plus G2 over CL. If I take the product of those two, the gain bandwidth product, it becomes, this cancels, and it just becomes minus GM1 over 2 CL. Clear? Okay, so we notice that compared to the quarter circuit, which had a gain of minus GM1, so what did that quarter circuit have as a gain? We have an ideal current source biasing it. Remember the gain of the quarter circuit is equal to minus GM1 over SCL plus G, right? So if you look at the gain of the differential circuit, we've got a factor of 2 in the denominator here. That's due to the fact that we only end up getting half of the differential input in to the differential circuit. And we have another term here. Instead of just G1 or G, we've got the sum of 2. So if these were equal, we're going to get a factor of 4 reduction in gain over what we had for the quarter circuit. Is that clear? If G1 and G2 are the same and they're equal to G, then it would be minus GM1 over 4G. So we got a factor of 2 reduction in gain, since only half of the differential signal is applied here. And then we have more reduction of gain since the denominator increases because of G2. The reason G2 is there is we're replacing that current source on top with a non-ideal current source. Okay. So that's our gain expression. And we observed what the gain was, the bandwidth, and the gain bandwidth product. If I want to, I can take this half circuit now. That half circuit has an input here. It has an output here. So it is also a 2-port. And it can be characterized by a GM and a G. Of course, now this G will be G1 plus G2, and this GM will be GM1 over 2. Okay? So we can easily move back and forth between the 2-port model of the quarter circuit and the 2-port model of the half circuit. And that's what I'm showing here. Let's compare the bandwidth now also. So we said that if G1 equals G2, we don't necessarily know why we want to make them equal. We'll look at that in a minute. I'm just saying if G1 is equal to G2, then we get a factor of 2 reduction in the gain because of this G1 plus G2, and a factor of 2 reduction in this numerator because of the differential input. So the bandwidth will be G1 plus G2 over CL. And the bandwidth, how does the bandwidth compare to what we had before? If the G's are equal. It what?
Double.
It doubles. So if the G's are equal, if G1 and G2 are equal, the gain drops a factor of 4, the bandwidth goes up a factor of 2, so the gain bandwidth product will drop by a factor of 2. Gain up 4, bandwidth down 2, gain bandwidth product down 2. Oh, I say if G1 equals G2, we're going to show that this often occurs as well. Or we can make this occur. Now, I should emphasize, I've not looked at any quarter circuits yet. This is true for any quarter circuit. We looked at this circuit where we bias it in the tail. If I bias the tail with a current source, if I bias the tail with a voltage source, how does the half circuit of this compare to the half circuit of this? They're the same because the voltage on the axis of symmetry is always 0, right? So consequently, this circuit and this circuit have exact expressions for the differential gain, exactly the same expressions for the bandwidth, exact expressions for the DC gain, and exactly the same expressions for the gain bandwidth product. Irrespective of whether you bias it in the tail with a current source or a voltage source. Hey, we're analyzing a whole bunch of circuits pretty quickly, aren't we? We don't go back and reanalyze these circuits again. We make an observation about what these different circuits' characteristics are. We'll see this later. So if they both have the same gain, the question is, does it make a difference which one we use? Whether we bias it with a voltage source or a current source. Tail voltage biases are not suitable for large common mode input range. So we're going to look at situations where we want to apply large common mode inputs. If you have a tail voltage bias, it won't work. Tail current provides good common mode input range, but at the expense of a modest reduction in output swing. So these are the trade-offs between tail voltage bias and tail current bias. Theorem. How is it different from what we had before?
It's connected to counterparts.
What?
There's a common bias between the counterparts.
That we had before. What we just got done analyzing was this circuit.
This one's fully differential.
It's fully differential on both the input and the output. Okay. So now we have differential outputs. Here are the two singulated outputs. Here's the differential output. Theorem. For any symmetric circuit with symmetric outputs, they're symmetrically located, and differential excitations, the differential voltage gain is double that of a single-ended structure. So you want to get the differential gain, just take that as a singleton structure, multiply it by 2. The bandwidth is the same. Since the bandwidth is the same and the differential gain is double, the gain bandwidth product will be doubled. Okay? We've analyzed a bunch more circuits, haven't we? We now have the fully differential input and the fully differential outputs. Any questions so far? Has everything we've covered looked real simple? Everything we've covered, great. Hopefully it looks real simple. If it doesn't, come and see me or raise your hand. We've covered a lot of territory with these observations. Now I'd like to get to the transistor level. So the first thing I'm going to look at is the 5 transistor op amp that's going to be derived from a single transistor quarter circuit. So consider initially the basic single-ended amplifier. I made a statement earlier that if you have single-ended amplifiers, the basic single-ended amplifiers, we're going to obtain the characteristics of the op amps that we get from these by inspection. So here's our, what was another name we had for the structure? Common source amplifier. And so here's what I put in green here is what? The quarter circuit, treating it as a quarter circuit, or as a 2-port. If I let the P device be the counterpart circuit, doesn't have to be, but I'm going to let it be the counterpart circuit. Then I have, everybody recognize the counterpart circuit of this? Replace N's with P's and P's with N's. Replace VSS with VDD. And now I'm going to bias this with a voltage source, DC voltage source, rather than with the input. And by the way, this circuit on the right is a practical implementation of the circuit on the left. We don't have good ideal current sources. What happens is this counterpart circuit is acting like a current source, a non-ideal current source. So there's the counterpart circuit. So we know that any half circuit can be modeled as a 2-port with a parameter GM and G, where G is equal to G1 plus G2, and where GM is equal to GM1. So I guess what's left, if I want to get this 2-port model of a half circuit, is to get GM1 and G1 for this circuit, and get G2 for this circuit. And if I create the half circuit, as I've shown here, and then reflect it, I get a fully differential operational amplifier. Here I'm showing it with a single-ended output, could have differential output as well. So let's look at the quarter circuit. What is the GM for this quarter circuit? So I have this quarter circuit that's now comprised of a transistor. Before it was a general quarter circuit, but now this quarter circuit is comprised of a transistor. And I remember I needed the parameters of this quarter circuit. I need capital GM1. And what's that equal to?
For this GM equals, should be 2. You could say it as 2 IDQ over VX is 5.
It's what?
2 IDQ over VX is 5 for the end.
Let's stay in the small signal parameter domain first.
Oh.
It's GM with this device. So it's GM 1, the GM of the transistor. And what's big G1 for this device?
G out. GM
G out 1?
plus GM.
No, this is just G1. And for the counterpart circuit, this is the DC ground here. What's GM for this circuit? 0. And what's G2? G out 2. Okay. So now we have this 5 transistor op amp, and the voltage gain was equal to minus capital GM1 over 2, which is equal to minus small signal GM1 over 2, divided by SCL plus G1 plus G2, which is G out 1 plus G out 2. I've analyzed at least part of that problem 5 in the homework assignment. Under the assumption that the two sides are matched. And under the assumption I have differential excitations. How long did it take? We wrote it down by inspection. Right? Is that where we're at? Everybody with me where we're at? We're almost analyzing that circuit. That's the homework problem. And we've got probably the parameters of most interest, the difference mode gain. The DC gain is minus GM1 over 2 G out 1 plus G out 3. Oh, I had a 2 here. I called this M3. This one M3, so I should have called this 3. This was M3, and this was M1. So here's the bandwidth, and here's the gain down product. Any questions so far? Yes?
We got V out as minus GM1 by 2. It is only single output, right?
It's what?
It is only single output.
Yeah.
We don't need different.
Right. You can ask the question, what's the differential gain? We know how to get that too. Right now I'm just getting the single-ended gain. Differential input, single-ended output. If I look at the differential output, I just put a factor of 2 in there. Right? Now, this circuit has a challenge. We're not going to worry about the challenge right now, but I'm going to point it out. If you want to bias this circuit, if you put a DC voltage here, there's a current that flows here. If this circuit is symmetric, this current here will split equally here and here. So this current here will be exactly half the tail current. If I look on the top, if I fix the voltage VB1 relative to VDD, this current here will be fixed. Now, what happens if those two currents aren't the same? What if half the tail current is not equal to the current on the right-hand side?
We lose our symmetry.
What?
We lose our symmetry.
It's symmetric.
But if the
Current on the bottom is determined by parameters of this transistor and VB2. The current here is determined by parameters of this transistor and VB1. I can adjust VB1 or VB2 conceptually so that those currents sum exactly equal to the tail current. But if I changed this voltage very slightly or this voltage very slightly, or change W or L of this very slightly, they wouldn't be the same. Is that a problem?
yeah.
We will violate Kirchhoff's current law if they remain in saturation. So if you build this circuit and you don't very precisely establish those two currents, then some of the transistors will drop out of saturation. This analysis we did is based on the assumption of operating in saturation. It's where the high gain mode of these devices are at. So things will drop out of saturation and the gain will be horrible. Does that make sense? Okay.
I have a quick question about the tail transistor.
Yes.
So if the drain of that transistor is sitting on the axis of symmetry,
Yes.
and we've been claiming that the voltage at the axis of symmetry is 0.
AC voltage to active symmetry is 0.
Oh, okay. Then that answers my question.
Okay. Good question. Any other questions? By the way, keep asking questions like that. Those kind of questions are the kind of questions we want. If anything doesn't make sense, you need to bring it up so we get it resolved. So what we've done is we've synthesized a fully differential op-amp from a quarter circuit. If you look at most textbooks, this circuit appears. They say, here's an op-amp. Did it appear here? No. We synthesized it from the quarter circuit. We've obtained analysis for the fully differential op-amp directly from the quarter circuit. We wrote down these gain expressions, the gain bandwidth product, and the bandwidth by inspection. We still need to determine what happens if the input's not differential. Right now we're looking at differential input. We'll address that issue later. Let's talk a little bit about biasing that circuit, because we said the circuit has a biasing issue. A circuit we put in to do the biasing is typically called a common mode feedback circuit. And what we'll do is we will typically bias VB1 with some convenience method, and then have some circuit that will adjust, will automatically select VB2, or we'll pick VB2 by some method and have some circuit that generates VB1. That circuit that does that is called a common mode feedback circuit. And here's a picture of what that looks like. So in this case, I'm going to fix VB2 to start with. And I'm going to put the common mode feedback circuit in here. What it's going to do is going to look at the voltages here and here. And it's going to take the average value of those two voltages. And it's going to compare them to what we would like it to be. And if the average value of these is different than this, it will increase or decrease VB1 until the average value of these voltages is what we want it to be. So a circuit that does that is called a common mode feedback circuit. The common mode feedback circuit is used to bias this structure. The common mode feedback circuit determines the average value of the two drain voltages, or the four drain voltages. It compares the average to the desired drain voltages. It establishes a feedback signal VB1 to set the right cue point. Now, I'm showing it here by feeding back to establish VB1. I could do it the other way around. I could fix VB1 and let the feedback circuit adjust VB2. It makes no difference which way I do it. So right now, let's not worry about the fact that there's a sensitivity biasing issue here. We have a way to solve it. We'll come back and look at circuits to that a little bit later. Make sense? Let's now start to address the question of what happens when you have a common mode signal present. And we're going to show that if we combine a difference mode and a common mode analysis, then we will get the analysis that we need for the problem 5. We've actually done the hard part already for problem 5 on the homework. We've done the hard part, we haven't worked very hard to do it. Now, if I'm repeating stuff you already know, please let me know that. So consider an output voltage for any linear circuit with two inputs. We have two inputs, A and B, and an output voltage V out. By superposition, if it's a linear network, we can say the output voltage is equal to V1 times the transfer function from the input to the output, plus V2 times the transfer function from the second input to the output. We can call these transfer functions a gain if we want. They can be DC gains, they can be AC gains, or whatever. What allows me to write this equation?
Linearity.
Linearity. Any linear circuit, you can use superposition to find the output. I'm going to define the common mode and different mode inputs by these expressions. These are definitions. The common mode input is the average of the two inputs. And the difference mode input is the difference of the two inputs. So if I take these two equations, I can plug V1 in here, and I can observe that V1 is equal to V common plus VD over 2, and V2 is equal to V common minus VD over 2. Make sense? So this is just a mathematical manipulation. So, in place of V1, we said V1 was equal to V common plus VD over 2. I can plug that in here. And in place of V2, I said it was V common minus VD over 2. I can plug that in here. And this is an alternate equivalent expression for the output. And now I can regroup terms here, and factor out the V common times A1 plus A2. Factor out the V difference, A1 minus A2 over 2. Okay? So this is an alternate equivalent expression for the output voltage. Now I can define the common mode gain, A common, to be A1 plus A2. I can define the difference mode gain to be A1 minus A2 over 2, by definition. So I substitute those in here. I get the output is equal to A common, V common, plus A difference, V difference. What are we going to do now? By the way, have people gone through this? Have you guys all gone through this before?
I think it's at 2:30.
Did it a little bit at 2:30? So the implication of this observation is that we can solve a linear two-port circuit by applying superposition either with V1 and V2 as the inputs, or with V common and V difference as the inputs. If I let V common and V difference be the inputs, I can first let VD go to 0 and find AC by putting a common mode input in. And then I can let V common go to 0 and find AD by putting VD in, and then add the two results together. Okay? In a circuit, when A2 is equal to minus A1, where the gain from the plus terminal equal minus that from the minus terminal, then we're going to find that the common mode gain, if A2 is equal to minus A1, the common mode gain is going to be 0. And the output is simply the difference mode gain times VD. The analysis we've done to this point of the op amps has been restricted to differential inputs, right? So basically, what I've calculated up to this point is the difference mode gain. If I now calculate the common mode gain, then I can get the overall output of the circuit. So how do I excite the networks in the common mode, the difference mode? So here's how I would normally apply superposition. I put V1 and V2 in, right? Or if I want to put V common and V difference in, I take two voltage sources here and two voltage sources here. And notice that when VC equals 0, I'm exciting it differentially. And when VD equals 0, I'm exciting the common mode. So here's the circuit I will use to calculate the common mode, the difference mode gain. I either let both VDs be zero, or I'm sorry, let VD be zero, or let VC be zero. They're not really two sources, they're really the same source. This is applicable to any linear circuit with two inputs and a single output. However, op amps often have symmetry, and the symmetry will further simplify the analysis. Theorem. So this is an extension now to differential outputs and symmetric circuits. The op amps we look at have symmetric outputs and symmetric circuits. Theorem. The differential output for any linear network can be expressed as V out equals A1, V1 plus A2, V2, or as A comma, V comma plus A differ, V differs. We saw that before. This theorem is what's important. The symmetric differential output voltage for any symmetric linear network excited at symmetric nodes can be expressed as AD VD. There's no AC there. Why is there no AC there? What? Why is there no AC VC there? What?
Because of the line of the symmetry.
Because the line is symmetry. A1 is equal to minus A2 because of symmetry. If A1 is equal to minus A2, A common is equal to 0. So all we're left with is this. So that analysis we just did for that 5 transistor circuit, are we done with the analysis of that circuit? But that circuit's symmetric. And so the common mode gain is 0. Here's a proof. It's easy to do it by superposition. I won't go through the proof there in the notes. Does anybody have any questions? We've covered a lot of territory. So hopefully, if you go back and look at the notes, if it wasn't clear what we've talked about, that will help a lot. Thank you very much.